November 5, 2018. In a control room at NASA's Jet Propulsion Laboratory in Pasadena, California, a group of engineers and scientists stare at a screen. For months, they had been watching the data from Voyager 2, a spacecraft launched 41 years earlier, shift, change, and build towards something. And then, in less than a single day, it happened. The readings flipped. The solar particles vanished. The cosmic rays spiked. Voyager 2 had crossed into interstellar space, and almost immediately, it started sending back data that nobody could fully explain. Today, we're going deep into the story of Voyager 2, Voyager 1's twin, launched just 16 days before it in 1977, and the genuinely puzzling things it detected as it crossed the boundary of our solar system. We're going to talk about a magnetic field that shouldn't behave the way it does, a boundary that turned out to be leaking in both directions, a plasma temperature that was hotter than any model predicted, and a mystery about the shape of the heliosphere itself that scientists still haven't solved. None of these are fringe theories. They come straight from 5 peer-reviewed papers published simultaneously in the journal Nature Astronomy. The science is real, and the questions it raises are extraordinary. To understand why Voyager 2's data is so scientifically important, you first need to understand what makes it different from Voyager 1. They launched within weeks of each other in 1977. They were built by the same team, with the same technology, for the same mission. But they took different paths. Voyager 1 flew by Jupiter and Saturn, then arsed upward, northward relative to the plane of our solar system, heading toward interstellar space on the leading edge of the heliosphere, the front of our sun's protective bubble as it plows through the galaxy. Voyager 2 took a longer route. It swung past Jupiter, Saturn, Uranus, and Neptune, the only spacecraft ever to visit all 4 outer planets, before heading out through the southern flank of the heliosphere. 2 different exits. 2 different That difference is crucial. When Voyager 1 crossed into interstellar space in 2012, scientists had no way to know if what it observed was typical, or if it was just a quirk of that specific location and that specific moment in the sun's activity cycle. Voyager 2 gave them a second data point, a second set of eyes in a completely different place, at a completely different time. Ed Stone, the Voyager project scientist at Caltech, who has worked on the mission since its inception, said it plainly. Without Voyager 2, we wouldn't know if what we were seeing with Voyager 1 was characteristic of the entire heliosphere, or specific just to that location in time. Now we had 2 probes in interstellar space, and what they found, when compared side by side, produced more questions than answers. There's one more thing that makes Voyager 2 uniquely valuable as a scientific instrument. Back in 1980, Voyager 1's plasma instrument, the tool designed to directly measure the temperature, speed, and density of plasma, stopped working. So when Voyager 1 crossed the heliopause in 2012, scientists could only infer its plasma measurements indirectly, through other instruments. Voyager 2's plasma instrument still works. It has been functioning continuously for nearly 50 years. Which means that when Voyager 2 crossed the heliopause in 2018, it became the first spacecraft in history to directly measure the plasma on both sides of the boundary, from inside the heliosphere into the cold of interstellar space. That data is irreplaceable, and some of it doesn't match what we expected at all. On November 5, 2018, Voyager 2 crossed the heliopause, the boundary where the sun's solar wind ends and interstellar space begins, and it crossed it fast. Scientists had expected a gradual transition, a slow blending of environments. Instead, Voyager 2's instruments recorded the entire crossing in less than 1 day. In the span of a few hours, everything changed. The solar particles surrounding the spacecraft plummeted. Cosmic rays, high-energy particles from distant exploding stars, surged dramatically. The probe had clearly entered a new environment, abruptly and definitively. Don Gurnett, a physicist at the University of Iowa, and one of the lead authors of the Nature Astronomy papers, described it this way. The old idea that the solar wind will just gradually be whittled away as you go further into interstellar space is simply not true. There is a distinct boundary out there, a hard edge. And it's astonishing, he said, how fluids, including plasmas, form such sharp, well-defined boundaries. The heliosphere isn't slowly dissolving into the galaxy. It ends, like a wall. But what Voyager 2 found on both sides of that wall raised immediate questions. Just before the crossing, its instruments recorded a strange compression layer, a region about 1.5 astronomical units wide, where the plasma was slowing down, heating up, and becoming twice as dense as typical solar wind plasma. Something was squeezing the heliosphere from the outside, and scientists are still not entirely sure what it is or exactly why it behaves the way it does. Let's talk about the first major discovery that left scientists scratching their heads: the magnetic field. Before Voyager 1 crossed the heliopause in 2012, scientists expected the direction of the magnetic field to change when it moved from inside the heliosphere to outside. Inside, the field is shaped and dominated by the sun. Outside, it should be shaped by the galaxy, and based on other observations, the galactic magnetic field should point in a noticeably different direction. It didn't change. Voyager 1's magnetic field just outside the heliopause was almost perfectly parallel to the field inside. Scientists were puzzled, but they wondered. Maybe it was a coincidence. Maybe Voyager 1 just happened to cross in a peculiar spot. Voyager 2 crossed on the complete opposite side of the heliosphere. Different location, different time in the sun's activity cycle, and its magnetometer recorded exactly the same thing. The magnetic field just beyond the heliopause was again largely parallel to the field inside. Leonard Berlanga, the NASA scientist who led the magnetic field study at Goddard Space Flight Center, put it plainly. We have to come to some understanding of why the magnetic field doesn't change. There must be some process causing this alignment, and that process, as of today, is simply not understood. This isn't a small discrepancy that can be smoothed away. Two completely independent data points, on opposite sides of the solar system, producing the same unexplained result. What makes this especially puzzling is what it implies. If the galactic magnetic field aligns itself with the sun's field right at the boundary, that means the sun is somehow influencing the magnetic structure of the galaxy outside its own bubble. The heliosphere isn't just protecting us from interstellar space, it's bending the fabric of the local galaxy around itself. The reach of our star extends beyond its own borders in ways we are only beginning to understand. The second major surprise: the heliosphere leaks, in both directions. Scientists had thought of the heliopause as a firm, relatively sealed boundary, the sun's last line of defense against the interstellar medium. The reality is messier. Voyager 1, as it approached the heliopause from inside, detected tendrils of interstellar particles that had somehow punched inward through the boundary, like tree roots forcing their way through concrete. Voyager 2 saw something different but equally unexpected on its way out: a trickle of solar particles slipping through the heliopause and leaking into interstellar space, extending more than 100 million miles beyond the boundary. The heliosphere, it turns out, is porous, and interestingly, it leaks more in some places than others. Voyager 1 crossed near the front of the heliosphere, the leading edge, where it collides head-on with the interstellar medium. Voyager 2 crossed closer to the flank, the side, and the flank, it turns out, is significantly more porous than the front. Stamachios Krimiges of the Johns Hopkins University Applied Physics Laboratory described it this way: Voyager 2 crossed in an area where material from inside the solar bubble was leaking upstream into the galaxy. That is very different from what happened to Voyager 1, which crossed at a time and place where hardly any material was leaking out. The heliosphere is not a uniform shield. It's a dynamic, asymmetric structure, and we have only measured 2 points of it. We don't know what the rest looks like. And then there's the temperature anomaly, the third major surprise. Scientists expected the plasma just outside the heliopause to be cold. Space between the stars should be frigid, right? And broadly, it is. The interstellar plasma is significantly colder than the plasma inside the heliosphere. But Voyager 2's plasma instrument, the one that Voyager 1's no longer had, measured something unexpected at the boundary itself. Right there, in the transition zone just beyond the heliopause, the plasma was hotter than any model had predicted. Not warmer than inside the heliosphere, still colder overall, but noticeably hotter than the undisturbed interstellar medium further out. Something is heating the plasma right at the edge. Something is adding energy to that zone that our current models cannot fully account for. The leading theory involves the compression of material at the boundary, but scientists are honest that the full picture isn't clear. Here's the uncomfortable truth all of these findings lead to: we still don't know what our own solar system looks like from the outside. For decades, scientists assumed the heliosphere had a long, comet-like tail, stretched out behind the sun as it moves through the galaxy, the way a comet's tail streams away from the sun. Some newer models suggest it might be more spherical. Others propose it could be shaped like a croissant, a flattened, rounded form with 2 lobes curving back on themselves. We genuinely don't know. Both Voyager probes exited from the head of the heliosphere, the leading side. Nobody has ever crossed the tail. And the tail, if it exists, might extend for hundreds of astronomical units, so far that even if we launched a new probe today, it would take generations to reach it. Don Garnett put the challenge plainly: we only have 2 crossing points. 2 examples are not enough to understand a structure this large and this complex. The heliosphere is roughly the size of a small star system. We've poked it with 2 thin needles, and are trying to understand its entire shape from those 2 puncture marks. It's like trying to describe an ocean after dipping your finger into it at 2 spots. What Voyager 2 confirmed, emphatically, is that the heliosphere is stranger, more asymmetric, and more dynamic than anyone imagined, and what lies just beyond it is stranger still. The interstellar space just outside our solar system is not the smooth, quiet void of textbook diagrams. It's turbulent, magnetically complex, hotter in unexpected places, and leaking material from our own sun. Both Voyager probes are running out of time. The nuclear batteries powering their instruments lose about 4 watts of power every year. Engineers have been shutting down systems one by one to keep the science instruments alive as long as possible. At some point in the next few years, the exact timing depends on how carefully power is managed, the last instrument will go dark, and the Voyagers will become silent ambassadors, still flying, still carrying their golden records, but no longer speaking. When that happens, we will lose our only eyes in interstellar space. The next closest operational spacecraft, New Horizons, will fall silent itself before it ever comes close to the heliopause. There is currently no approved mission to replace the Voyagers in interstellar space.